So I'll talk about robot learning, but before we go to robot learning, let me say a few words about myself. So I was doing research in algorithmics theory for a few years. This is what I was doing during my PhD studies. This is also what I was doing during my postdoc and my first years after going back to Poland at the University of Warsaw. But in recent years, I turned and my research pivoted to machine learning and then more towards machine learning in robotics. In particular, very recently, just a couple of months back, we have installed the first robot at the university. So we have a lab, which is also sponsored by a company which I co-founded, which is called No Magic. And the focus of this lab is exactly on robot learning, which I'll explain on the next slide. What is it about? Currently in the projects that are developed by the lab, a few people are already engaged. This is Krzysztof Ciepiera, who is a faculty member at the University of Warsaw Institute of Informatics, and also a few students, both masters and PhD students, Piotr Krzywicki, Karol Pieniądzy, Jakub Świętkowski, and Piotr Tempczyk. So I'm happy to have a small group that I'm working with, and our plan is to build the base towards having very interesting and good experiments, and then expand and enlarge the group. So what is the field about? So robot learning is defined as an intersection between machine learning and robotics. So there is this robotics component, which doesn't necessarily mean that there has to be a physical robot, because you can do robot learning in simulation. So in particular, games and research in reinforcement learning also fits this description. But for me, the most interesting part is manipulation, in particular manipulation in the real world. So this is why we bought a manipulator. This is UR5E. So this is a collaborative robot. We have a gripper that can grasp objects with 2 fingers, and now we also have another one which we can use to grasp with suction, and we'll be performing different experiments involving manipulation. So the goal is to use an object and somehow change the state of an object. And the simplest thing and the most basic problem in robotic manipulation is grasping. Like the robot is presented a set of objects, and it needs to pick an object and move them to some other place. So this sounds very basic, but this problem is not yet solved, and there has been a tremendous progress in the last few years, mainly because of what has happened in the computer vision community due to the AlexNet paper, and then following papers for image classification, object detection, segmentation, and so on. And this wave also went to robotics, and then this is when the robot learning field actually emerged. So the 2 fields of interest that I'm working with on the most are robot learning, especially manipulation, and computer vision, because we also have some projects that are purely on the computer vision side, which is of course very useful in robotics, but we can develop our ideas and test them purely on the computer vision datasets, so not necessarily involving the robots. So how can supervised learning be connected to robot grasping? So I would like to give you a flavor how this grasping problem is connected to the problem of supervised learning. So I guess you already know that in supervised learning, what we have is we want to train a model that will perform a mapping from input to output. So for any single input, there is a very precise output that we want to predict. And for the problem of robot grasping, it's a priori not clear what is mapped to what. And one of the ways to go around this is use what is called a top grasp. So assume that we have a robot that is overlooking a table, and there is a camera which allows the robot to see. And what we need to decide is where to perform a grasp, like where to move the fingers of the robot so that the robot will then go down, clip the fingers, and move up, and hope that this way it will grasp some object. This way, we can specify the grasp by using just a few parameters, and those parameters necessarily need to be the pixel coordinates. So we need to choose where to grasp, but also how to rotate the fingers. So assuming that we want to grasp with 2-finger gripper, we need to decide where the fingers needs to go, and this is expressed by this axis, and in particular with this angle here. But assuming that the grasp is parallel, which we can achieve by rotating the image, then a single grasp can be characterized just by the position of the pixel, which means that we can then cast the problem in the supervised learning setting, where the input is the image, that this is what the robot sees. And now the output is, for each pixel, we want to decide if the robot is about to grasp in this particular place, will this grasp be successful or not? And we can collect a data set of successful and unsuccessful grasps and train a model on this data set. And then this model will be able to predict for a new scene where to grasp. So this is the connection. Now, my hope, and this is what I would like to explore in the next year or two, is semi-supervised learning. So what is semi-supervised learning? In semi-supervised learning, we are given more data than just the labeled data set. We are also given a part of the data set that is potentially larger or usually larger, but it's unlabeled. So we don't know what are the correct set of labels. So for the computer vision problem, imagine that we want to classify images, and we have some set of images that we don't know what the label is. But even if we don't know what the label is, we can use the following trick. And this is one of a few tricks. I don't have much time to cover them all, but this is one that I find really elegant. So the trick is as follows. So you take an image for which you don't even know what is on the image, but then you take another copy of this image that is augmented. In this particular case, it's flipped and it's changed from RGB to grayscale. Now you put both copies through your model that you're currently training, and you see what is on the output. And on the output, you'll have two different distributions. They might be potentially the same, but usually they will be slightly different. And if we know that the objects on those two images is actually the same, because we started with two copies of the same image. So we want the classification to be exactly the same for both of those copies. So then what we can do is we can apply what is called the consistency loss. So we would have to formally define how to do it, but the point is that if the model predicts something that is different on one copy and something that is different on the other copy, then we can tweak the model a little bit and push it towards predicting the same class for both copies. And we can do this even if we don't know what the correct label for this image is. And there have been a few papers published during the last 12 to 18 months. Very interesting papers, some of which you may have heard, like SimClear, Moko, but many others as well. And they push those ideas for semi-supervised learning very far. Now, how this is involved and what we can do about this in this robot learning field, and in particular in the project that we are working on. So we are currently working on, I would say, 4 projects. First is purely on the computer vision side. So we are interested in semi-supervised learning for object detection. So in object detection, you are given an image and you need to not only classify, but also locate on the image where the given object is, and using a bounding box, axis parallel bounding box. So here we assume that we have the data set that is labeled, but on top of this, we also have a large data set that is unlabeled. And we are performing experiments. We have some ideas how we could go around this and exploit this unlabeled data set. So in this semi-supervised setting, we'll obtain better results than in just purely supervised setting. Now, we are also trying similar ideas in the world of manipulation, in the world of robot grasping. And again, here we would like to use, for example, the images that we can do using the camera, but without grasping, or using the data about objects that are not currently grasped. So the robot sees much more than it interacts with, because typically the robot is given a number of objects and it tries to pick only one, but the other ones are also on the scene, so we may try to use this data somehow. Another project that we are working on is to improve the strategy of picking many objects one after the other. So we imagine that we have a bin of objects and we need to clear it. So we need to pick all the objects from the bin. But now what typically happens is you try to pick at the point which has the highest confidence given by the model. But the problem is what happens if the model is wrong, and what is our strategy afterwards? Because the model suggested some place which is incorrect. And we have a few ideas and different strategies that might be beneficial, what to do after a failed grasp. Another problem which is slightly different, and this is where Karol Pieniądz is also involved, because he has background in drones much more than I do, because actually I don't know much about drones. I'm more focused on computer vision and manipulation, but Karol is interested in docking a drone. So he would like to somehow catch a drone with a robotic arm, and the motivation for this is when you want to land a drone, you need quite some space in order to do this safely. And the goal here is to use a robotic arm which will catch the drone so that it can be parked with a limited space. So in particular, this robotic arm could catch more than one drone and somehow park them in a very succinct space. So those are the projects that we are currently working on. We've recently started, like the lab has started just a few months back, so we don't even have manuscripts for those, we have ongoing experiments. Yeah, but I'm pretty sure that we'll have very interesting results in the next few months. So I'm happy to answer questions now, and if you're interested, feel free to reach out to me. This is my email address, and yeah, that's it for this presentation. So if you have any questions, let me know.